The following video is on the fundamental theorem of calculus. We've been looking at how to find the area under a curve using the addition of areas of rectangles. We also saw in the last video how to calculate a Riemann sum, and you might have noticed that we use suspicious notation to represent the Riemann sum. We used that elongated S symbol that we had earlier used for antiderivatives. This is not a coincidence, and in this video we will see why. There's two parts to the fundamental theorem of calculus, and we will start with part 1. Let g of x be the integral from 0 to x of the function t dt. So here's, in purple, the function f of t equals t, and we know that if the function is positive, then the integral from 0 to x will be this red shaded region. So if x is positive, then this g of x is going to be represented by the area of the red shaded region. So g of 1, for example, is going to be the area of the triangle if x is at 1, which is 1/2 base times height, which ends up being 1/2. G of 2, if x is equal to 2, then the area of this red triangle would be 1/2 2 times 2, which is 2. And g of 3, if x was at 3, then the area of this triangle would be 9/2. In general, we can see that if we have some positive value x, the area of this triangle will be 1/2 x times x, or x squared over 2. So g is a function. Let's try to find the derivative of this function. So g of x, we said, was x squared over 2, and we know that the derivative of this would then be x. Notice that this is actually the function that we started with, f of t equals t. So in general, if g of x is the integral from a to x of f of t dt, and f of a is defined, then g prime of x equals f of x. In other words, the derivative is the actual function, just with x instead of t. Let's look at another example. So d by dx, or the derivative, of the integral from 0 to x of t squared minus 5 over t plus 2 dt. Now I have no idea what this function looks like. It's probably something super crazy, but we're taking the derivative of an integral. So I'm going to treat this t squared minus 5 over t plus 2 as my f of t, and the fundamental theorem of calculus says that all we have to do is replace the t's with x's. So we end up with x squared minus 5 over x plus 2. That's the final answer. Or let's try another one, d by dx of the integral from 1 to x of sine squared theta d theta. Notice it doesn't require that I start at 0, it just requires that I'm able to plug in the value 1 in this case into my function sine squared theta. So in this case, my function f of t is sine squared, or f of theta is sine squared theta, and the final answer is just sine squared x. So anytime I'm taking the derivative of the integral, I can just replace the variable, in this case theta, with x. Let's try another one. d by dx of the integral from x to 1 of sine squared theta d theta. Notice that this is almost like the previous one, except my bounds have switched. We saw in the previous video that if I want to switch the bounds, I have to pull out a negative sign. So I pull out a negative and switch the bounds, and I'm left with negative sine squared x. Let's try another one. d by dx of the integral from 1 to x squared of sine squared theta d theta. The fundamental theorem of calculus only tells us that we're allowed to do this if instead of an x squared, if I had an x. So I'm actually going to do a u substitution here. So I'm going to do the chain rule, where we use x squared as our inside function. So I'm going to take the derivative of the outside, which is the integral from 1 to u of sine squared u, or sine squared theta d theta. So I get sine squared of, in this case, x squared. But then I have to do times the derivative of the inside thing, which is 2x. Or I could do something crazy like d by dx of the integral from cosine x to 5 of 25t squared over t plus 5 dt. Notice that the x value is not in the top of the integrand. So I first have to switch the order, and then I have to do a chain rule. So first, instead of t's, everywhere I have cosines, and then at the end I multiply by the derivative of cosine, which we know is negative sine. Part 2 of the fundamental theorem of calculus says that if f is continuous on a closed interval from a to b, and capital F of x is the antiderivative of little f of x, then the integral from a to b of f of x dx is capital F of b minus capital F of a. This is the most amazing part of the fundamental theorem of calculus. We've been spending all this time and energy working on Riemann sums, and you've probably come to the conclusion that Riemann sums are tedious and a lot of work. This actually allows us to just use antiderivatives to evaluate Riemann sums. So, in other words, if we have the integral from a to b of f prime of x dx, I'm just going to take f of the top value, which is b, minus f of the bottom value, which is a. And that is the area, or the Riemann sum, under the curve. In other words, derivatives and integrals are inverse processes of one another. We saw in part 1 of the fundamental theorem of calculus that if we take the derivative of the integral, we get the original function. This part says that if I take the integral of the derivative, I get the original function again. So for example, let's take the integral from 1 to 4 of x cubed dx. We looked at this value in a previous video. Here we can use the antiderivative to solve it. So we take the antiderivative of x cubed, which is x4 over 4, and then to indicate that I've already taken the integral, I write a bar to the right-hand side with a 1 on the bottom and a 4 on the top, indicating my two bounds. Now I plug in the top bound, which is 4, minus, when I plug in the bottom bound, that's a 1. So I get 4 to the 4 over 4 minus 1 to the 4 over 4, which is 256 over 4 minus 1 over 4, which is 255 over 4. Notice that this is the exact same answer that we got in the previous video. The important thing, though, is that this is so much easier than what we did in the previous video. Before, we took almost an entire slide and several minutes of work in order to get this answer. Here, it just took us a few seconds and some very simple arithmetic. Let's try another problem. So the integral from pi to 2 pi of sine theta d theta. We first take the antiderivative of sine theta, which is negative cosine theta, and we draw a bar to the right-hand side with a pi on the bottom and 2 pi on the top, indicating our bounds. We then plug in the top bound first, minus what happens when we plug in the bottom bound. And cosine 2 pi we know is 1, so negative cosine 2 pi is negative 1. Cosine of pi is negative 1, so I'm going to get a plus negative 1. So I end up with negative 2. Let's try another one. The integral from 1 to 2 of x squared plus 5x minus 3 dx. We take the antiderivative of each part one by one, so the antiderivative of x squared is x cubed over 3. The antiderivative of 5x is 5x squared over 2. The antiderivative of negative 3 is negative 3x. And I draw the bar to the right-hand side with the bounds 1 and 2. Now I plug in the top bound, minus plugging in the bottom bound, and when I do the arithmetic, I end up with 41 over 6. This is so much easier than doing a Riemann sum. Finally, let's try the integral from a to a of f of x dx. Regardless of what the antiderivative is, we're going to get capital F of a minus capital F of a. And since capital F is a function, we know that f of a is going to be the same thing in both cases, so we're left with 0. That means that the integral from a to a is always equal to 0.